Okay. So today we shall see what is there are two types of filters in digital signal processing. They are FIR filter and IIR filter. FIR stands for finite impulse response filter. Finite impulse response filter. So what does this mean? Finite impulse response filter. It means that the impulse response, that is Hn, we know that impulse response is Hn. If impulse response Hn has a finite support, that means if Hn is, if you plot Hn, say 0 to, you have some values. If this have some finite values, say from 0 to n minus 1, if it have n values like this, and nothing else in this region, this value should be 0, this value should be 0, and this is a finite support, that is you have values only in this region. Then you call this, if you have finite numbers of impulses in the response, you call it a FIR filter. So basically an FIR filter will have an impulse response Hn which is finite. Now let us see some examples. Say Hz equal to, suppose you have Hz equal to say 1 plus Z inverse, which is the example we have seen earlier. Am I audible to all of you? Can you just give me a feedback by unmuting the mic, one of you?
Yes, sir.
Yeah, thank you. So Hz is 1 plus Z inverse. So if you take inverse Z transform of this, what you're going to get is inverse Z transform of 1 plus Z inverse is inverse Z transform of 1 is delta n. You know that inverse Z transform of 1 is delta n. And you, what is inverse Z transform of Z inverse? Can one of you tell? If Hz is 1 plus Z inverse, what is Hn? Inverse Z transform of 1 is delta n. What is the inverse Z transform of Z inverse? One has an inverse transform delta n. So 1 into Z inverse means, you know that x z into Z inverse have an inverse transform. If xz has inverse transform xn, then xz Z inverse will be having, you have Z transform of xn as xz, what will be the inverse Z transform of xz Z inverse? It will be xn minus 1. Delay is converted as Z raised to how much delay it is. So Hn will be delta n plus delta n minus 1. So if you plot this, Hn is at 0 you have one impulse. This is value 1, and at 1 you have another impulse having value 1. So this is the Hn. So this have a finite support and there are finite values. So you can call this as an FIR filter. So this was an example of FIR filter. Now can you tell what will be say Hn equal to, suppose Hz is 1 minus Z inverse, Hz equal to 1 minus Z inverse. Then similar to this, Hn can be found as delta n minus delta n minus 1. So if you plot Hn, it will be having at 0 you'll be having a value of 1, and at 1 you'll be having a value of minus 1. This is 1 and this is minus 1 into delta n minus 1, so magnitude of minus 1. So this is also finite, so this is also an FIR filter. So we shall see what are IIR filters. Before that, can you predict something on the stability of such FIR filter, whether they are stable or not? How will you find whether a system is filter is stable or not? Given Hz or given Hn, how will you find whether a system is stable or not? You have some criteria, right? So if your Hn is given, you can find whether it is BIBO stable, boundary input, boundary output stable, by finding sigma Hn over the whole support. If it exists from minus to infinity and varies from minus to infinity, sigma Hn, if this is say a finite value, you can tell that the system is stable or not. Okay, so if you have any doubt, please ask. Anyone can interrupt at any time and ask. So let me take say whether the system, or how do you find whether a system is stable from Hz? You have to find whether there are poles. If Hz is say Z minus Z0 by Z minus Z1 into Z minus Z2, where Z0 is the 0 and Z1 and Z2 are the poles. At Z1 and Z2, you know that this will tend to infinite value, which will make the system unstable. So at the poles, so in this case, poles are Z1 and Z2. At these poles, this system is going to be unstable. So like that, we can find whether a system is stable or not from Hn or from Hz. So in the case of FIR filter, can you tell whether the FIR filter has whether it has 0 or poles? FIR filter, we saw examples of FIR filter. Hn, we found it as 1, 1, and the two FIR filters that we have seen have the values 1, 1 and 1 minus 1 with 0 index at 1. So this, if you add this, will it be 0? Suppose you take sigma Hn, will this be 0? Okay, before that, let us see Hz. Hz is 1 plus Z inverse. The FIR filters that we have seen, Hz is 1 plus Z inverse and 1 minus Z inverse, the two FIR filters. Do they have any poles or do they have any zeros? What are the zeros or poles they have? What are the poles or zeros they have? Can one of you answer? Z equal to 1 plus Z inverse or Hz equal to 1 minus Z inverse. Do they have poles or do they have zeros? you can see that h z equal to 1 plus z inverse or h z equal to 1 minus z inverse, both of them don't have any denominator. So you can very well tell that this has just zeros, and if there are no poles, this is not going to be unstable at any values of z or z inverse. So that means this doesn't have any poles, and hence it is not going to be unstable at the values of the poles. So this system FIR filters, they will be always stable. They will be always stable. Now let us go to the case of IIR filter. What IIR filter is first? IIR filter is infinite impulse response filter. Infinite impulse response filter. So as the phrase indicate, infinite impulse response means Hn will be having infinite values. The support of Hn will be infinite. So that means at 0 it may have some value, say 3. At 1 it may have some value 1. At 2, say it have another value, say 5. And it will have infinite support. This is not finite. The support is not finite. You cannot tell that it's in this interval or this many numbers of values you have. It will have infinite numbers of response. So let us take some examples whether something like that is possible or not. So let us take an example of hz equal to 1 by 1 minus z inverse. Suppose hz is 1 by 1 minus z inverse, and suppose it has an ROC mod z greater than 1. So can you tell what will be Hn from this? One of you can unmute and tell what will be Hn. I'm audible to all of you, right? What will be Hn? Suppose Hz was, let's take another example. Hz was, say, 1 by 1 minus a z inverse, or this is same as z by z minus a. And suppose that ROC is mod z greater than a, mod a. Then can you tell what will be Hn? Please unmute and tell. Anybody can tell what will be
A raised to n u of n.
a raised to n u of n. Very good. A raised to n u of n. So similarly, can you tell what will be Hn here?
U of n.
U of n, just u of n, because a is 1. So this become u of n. Okay. So Hn is u of n means what will be the, how will you, if you plot Hn, it will be like this. At 0, you have a value of 1. At 1, again you have value of 1. At 2, again value of 1. Like that, it goes to infinity. So that means Hn is infinitely supported, or this is an, the filter corresponding to hz equal to 1 by 1 minus z inverse is an infinite impulse response filter, which is called IIR filter. So this is an example of IIR filter. Let's take some other example. Suppose you have, say, 1 by 1 minus say 3 z inverse. In that case, if HZ is this value and ROC is mod Z greater than 3, we can tell that HZ is or HN is a raised to n un, which is 3 raised to n un. And if you plot this at 0, you have value of 1. At 1, you have value of 3. Because we substitute for n equal to 1, this becomes 3 into un, so which is value of 3. At 2, you have a value of 3 square 9, like that it goes. And this is going to be also infinite, so this is also IIR filter. So you understood what is an IIR filter. Now if you see the stability criteria, stability of an IIR filter, so let us find, or let's take an example of HZ equal to 1 by 1 minus Z inverse. Does this have any zero or does it have any poles? We are concerned more about the poles than zeros. So what are the poles here? Equate the denominator to 0. So 1 minus Z inverse equal to 0. Then you get that Z inverse equal to 1 is one of the pole, or Z equal to 1 is a pole. So at Z equal to 1, this is going to approach, or this is going to tend to infinity. And hence, if you find yz, which is input Z transform multiplied by hz, this will tend to infinity, and hence yn will also tend to infinity. So this filter is not stable at Z equal to 1. So there are some criteria. So you cannot tell that IIR filter is always stable. It will be stable at some conditions. So IIR filter is not always stable. At some conditions only it is stable. So if you take Hn also, from this you know that Hn is having infinite impulses. So if we take sigma Hn square, then this is also going to be an infinite value, and this is not going to be bounded output. Okay, so this way you can tell that IIR filter is not always stable, but FIR filter is always stable. Okay, now FIR filter, I think this the FIR filter and IIR filter concept is clear to you. And let us take, say, 1 minus Z inverse itself. So yz equal to this hz equal to 1 by 1 minus Z inverse, you can write as yz by xz. This is 1 by 1 minus Z inverse, and if you elaborate this, this become yz minus yz Z inverse equal to xz. So if you take inverse transform of the whole thing, this become yn minus, this is yn, yz into Z inverse, its inverse transform is yn minus 1 equal to xn, or this you can write as yn equal to xn plus yn minus 1. So this kind of response of a system indicates that the system is IIR filter, because from the see, let us take the example of FIR filter. Here you have seen that Z is 1 minus Z inverse. Here also you can write it as YZ by XZ equal to 1 minus Z inverse. So if you cross multiply this, it become YZ equal to XZ minus XZ into Z inverse. If you cross multiply this, if you take inverse transform, this become yn equal to xn minus 1. So you can see that yn depends only on xn values and their shifted versions. So in those cases, you can always tell that this kind of filters are FIR filters. But if yn has a recursive relation with yn or its delayed versions, that is yn, as in the case we have seen here, yn equal to xn plus yn minus 1. Here yn depends on previous values of yn also, that is yn minus 1, yn minus 2, etc. In that case, this is going to be an IIR filter. So from the system response itself, you can tell that whether a system is IIR filter or FIR filter. Yeah, I think we shall stop today. I'll just take half an hour lecture today. You can take the remaining time for preparing the quiz today, which will be based on today's lecture. I think half an hour is okay today. I'll stop presenting now. Okay. So I hope you got the understanding of what is FIR filter and IIR filter. I'll share this recording. I'll stop recording now.